All right. You've always wanted to pass out?
I've always wanted to pass out.
I've never passed
If
out.
you knew you could pass out and wake up and not.
But I blacked out one time at summer camp in the showers.
I've gotten knocked out. I golfed.
All right. Okay.
And I was naked.
So back to this. So we need a point, which they give us is basically y of 5, and we need y prime, okay, of 5. So the whole equation of a tangent line thing is getting that information and then putting it into our point slope thing. So we got this, and we got this, and so we know what that 5 and negative 12 are going to go in there. It's just a matter of finding the slope, which is y prime. How do we find y prime on this? Okay, one way would be to get the y by itself. And actually, that wouldn't work too bad in this one. Now, thank God we're not taking the gateway test right now. Because I think we would be in a lot of trouble. That's one of the things we have to work on over the course of this chapter is doing these derivatives. Now, luckily, these problems mostly involve derivatives, so we're going to have to get better at it as we go through, okay, just by practice. But this would be implicit differentiation. This is just like one of those that we put on the gateway test where we do the derivative of both sides. That would be 2x. What's the derivative of y squared? 2y, y prime, and the derivative of 169 is 0. Okay, now we get the y prime by itself. So what Natalia said would have been just fine. We could have gotten y by itself first and then done the derivative, but you don't always have that option on these problems. All right, so we need to know implicit differentiation. So we divide by the 2y. We get negative 2x over 2y. We could cancel the 2's. That would be legal. And there's our y prime. So now we plug in our 5. But we not only have to plug in the 5, we have to plug in the negative 12 as well. So we put in the 5, that'd be negative 5. For the y, we put in the negative 12. So that would be a slope of 5/12. So our equation of a tangent line would be y equals 5/12, x minus 5 minus 12. Now, one of these has to equal that. Now it's just a bunch of algebra. And again, on this no calculator multiple choice section is the one that you expect to have to do a lot of algebra. You have to know your trig values. You have to know log graphs. You have to know all that stuff that I've talked about that you should know without a calculator. This is when they're going to quiz you on it. So yeah, it'd sure be nice if they would have wrote the equations in this order. We'd be done and we could match it. But now that you're going to have to show you can do a little bit of algebra. So you distribute this through here. You get 5/12x. Well, this might not have been the smartest way to do this. Probably would have been faster to do what there? What would have been a little smarter here maybe? If I had multiplied both sides by 12 and gotten rid of the fraction, okay? But this works okay. So we do this. Now I would say multiply everything by 12. So we get 12y equals 5x minus 25 minus 144, right? 12 times 12. And now I get the x's. Now I'm looking here, all of my x's, I know it's going to be one that's got a 5x in it, so I can get rid of that one, I can get rid of that one, I can get rid of that one. So it's going to have a 5x in it. So it's going to be one of these. I want the 5x to be positive, so I'm going to get everything over here. I'm going to have 5x minus 12y. Move that over here. This would be negative 169, so when I add it over to this side, that'll be positive. So it's going to be this one. Okay, negative 25 and negative 144 would be negative 169. So it's C. Okay, so there's a lot of algebra involved in that one, but we had to do implicit differentiation. That one probably takes more than 2 minutes, right? So hopefully you save some time on one of those, and then you can get that one. Okay, that was 9. What was another one you want to see? 13. Okay, let's do 13 and 16. We'll do 13 and then 16, and then if there are some other ones we want to see, at some point, maybe tomorrow, maybe the next day, whatever, maybe both, you know, at the beginning of class, I might say, hey, take out sample 1. Are there any questions that you have that we haven't talked about? Are there any of those we still need to talk about? So mark them, put notes right now. Obviously, we won't have time to go through every problem on every pack, Okay, so if you have questions other than what we do have time for class, and you should come in and see me. You shouldn't go through these packets and leave problems unanswered or problems that you don't still understand. You know, take time to at least look at the answer book and read their explanation, or talk to me or talk to a classmate. All right, 13. If the graph of f has a point of inflection at x equals -1, then the value of k is. Now these always tend to be ones that cause us difficulty as well when we see this k in here, and we kind of get panicky. Okay, what is that? All right. We get kind of panicky when we see this K in here, and that over the years, that's always tend to cause us difficulties, especially early on. Now, hopefully, we'll get better at these as we go along. The key is right here. What do you think of when you see point of inflection? Concavity. What else? No. Not the derivative of f of x would equal 0. The second derivative would equal 0, right? When you think about the chart, inflection points, concavity involve the second derivative. So where this graph is going to have a point of inflection is going to be when the second derivative equals 0. Now, they already told us where it was, but we don't know what k is, so k is the thing we'll be solving for. So what you have to do here is f prime. So again, now what I would do, if I would write this as k x to the -1, that would make this an easier derivative to do. Remember, k is just a number, so you just treat it like a number sitting there. All right, so tell me what f prime would be. 4x minus, okay, so that's f prime, but I need f double prime. 4 plus, right, k is just a number, so I bring that down in front. That'd be 2k x to the -3rd, and I want that to equal 0. Now, normally to show something's a point of inflection, we'd have to do a number line, we'd have to check on both sides, see if it changed the concavity, all that. On the multiple choice, you don't have to prove that it's a point of inflection. Matter of fact, they told you it's a point of inflection, so we don't have to worry about that. But it's where this second derivative is going to be 0. So now this is one of the reasons on the gateway test that I had you simplify things and work with that, because I think this one's going to be much better if we put an x cubed, put that x down the bottom like that. Now there's one more thing I can still do yet, because I still have two variables in it. I can put a -1 in for x, because they told me that's where the inflection point is going to be. So when I put a -1 in for x, -1 cubed is -1, so that makes this -2k equals 0, so that's pretty easy to see then that k is going to equal 2. Right? K is going to equal 2. Now, did anybody get a 2 doing that differently?
I think that's what I did.
That's what a bunch of people in the other class did too. Now, why did you do that? Was it because it had something to do with point of inflection, or was it because lack of anything better? You couldn't think of it. No, not lack of intelligence. Lack of anything better that you could think of. You couldn't think of anything better, so what? I'll put a -1 in for x. And several people in the other class brought that same thing up, and you do get 2. That's pure luck. Pure luck. Because think about it. If you put a -1 in for x, and then what'd you do? You set it equal to 0? Okay, so what you're saying, okay, we've never set the original equation equal to 0, but aren't you just saying that on the original graph, on the f graph, that point is at -1, 0? So what's happening is, and since you do get the right answer, what that is saying is that the inflection point on f happens to be right at the x-axis. So what was purely luck about that, it's okay to plug a -1 in for x, that's fine. But setting it equal to 0 was just kind of, why 0? Why not set it equal to 10 or 15 or what, right? I mean, because by what you're doing is putting in the y value of where the inflection point is, and we have no idea what the y value of the inflection point is, right? Okay, so that was just luck. That was just luck. Yes.
I was kind of confused on how to treat the base, so I actually plugged in each one and guessed and checked, and I found the double derivative of each one after plugging in.
To see if it was zero.
Yeah.
Oh, now that's a good strategy. Well, when you have multiple choice, you always do have that option of taking your answers and trying them in the problem. Sometimes that takes a long time, but if you have time, I wouldn't do that till I went through all the problems and maybe I have some extra time. Mark the problems that you have struggled with, and then come back to them. And if you have extra time, that might be something to do. But that sometimes can be a good strategy on multiple choice questions.
And also afterwards, because I first plugged in the first one, it was -2, and I found that it equaled 4 or something like that. So I realized if it wasn't a positive.
That might have made 0, and so you didn't have to maybe try all of them. So, but at least you did understand what you were trying to do. You did understand you were trying to do the second derivative, and you wanted it to equal 0. So that did show some understanding of inflection. Okay, let's go to 16. Now 16 does have to do with some stuff we're going to talk about today. We're going to be talking about motion. We're going to be talking about position, velocity, acceleration. All right, and that packet I gave you, that other packet, where there's a problem in there, we're going to talk about today. And I want you to see these connections of what we've learned before, and then hopefully that helps you with the new thing we have to do today. So this says a particle moves on the x-axis, and the reason we do this is because it gives us, when we do position, velocity, acceleration, it gives us a marked way to measure what our position is. We could be positive or we could be negative. Just like east of Bismarck and west of Bismarck. Remember that way back in the beginning of class we talked about that? Okay, it's the same scenario. We just talked about, it's just easier to talk about a particle on the x-axis. So these problems are all over the AP test. Okay, particle moving on the x-axis. It's just one-dimensional motion, right? Just one-dimensional motion. In this case, horizontal. All right. So they want to know, this is the position. They want to know the acceleration. We also have to get used to this idea of x. Since it's on the x-axis, that's its position. So we're doing position, velocity, acceleration. So in this problem, x would be position, x prime would be velocity, and x double prime would be acceleration. And that's what they want. So we have to do the second derivative, right? So how do I do, let's see, Kingsley, how about you? What is the derivative? How do we do the derivative of that? We do the quotient rule, right? No one would ever think of doing the derivative of the top and then doing the derivative of the bottom, correct? I'm picking on John because that's what he did this morning. He gave me a thought. Did anybody else do that? What's happening if you do that? You're not going to admit it, are you? Because I just made fun of him. What's happening when you do that? What are you doing? What are you thinking of? L'Hopital's rule, right? Obviously, we just got done talking about it, so of course you're going to think about doing it. Do the derivative top, but that was L'Hopital's rule. That's a whole different thing, right? We're back on thinking about what we did on the gateway test. And we want to do the derivative of this. We have to do the quotient rule. So x prime would be the derivative of the top, which is -1, the bottom left alone, minus the top left alone, times the derivative of the bottom, which is 1, all over the bottom square. And again, one of these problems is definitely going to take you more than probably 2 minutes by the time you get through it. But it does actually work out pretty nice. And on the gateway test, I said there are a lot of things you should do simplifying wise, and this is one of those problems why I said that. We're going to distribute there. We can't forget we got to distribute that negative sign. So that ends up being a plus t there. And then the bottom, I'll just leave it. We need to FOIL that out, and it turns out the t's cancel, which is nice. So we end up with simply -2 over 1 plus t quantity squared for our x prime. Now I need x double prime. Do the quotient rule again, or would that be silly? Nobody wants to. That would be silly. I don't like that. I don't like doing the quotient rule there when you have a constant on the top or the bottom, because then you usually forget the derivative constant 0. I think that messes you up. I think you should just move that up top as a negative power. So this is just -2, 1 plus t to the -2 power. That's your x prime. So now when we do x double prime, we simply bring that power down in front, which would be 4, leave the inside alone, to the negative third power times a 1, the derivative of the inside. And now we're going to have to do something with this, so I think it's best to take that negative power and drop it down to the bottom. So this is where we talked about simplifying. I know in the gateway test I would have made you do that. You would have just left it here. That would have been fine. But when we're going to actually use it and do something with it, I think we need it in this version. Okay? And they want to know the acceleration when t is 0. So what do? Put a 0 in for t. 1 plus 0 is 1. 1 cubed is 1. 4 divided by 1 is 4. So the choice is E. So in the end, it wasn't terrible bad, but that's what we have to do. So hopefully you get a little bit of sense of, yeah, we did the gateway test, we did derivatives, and then we moved on, but we didn't really move on. You've got to be able to do them. Okay? We will do another derivative test. You won't get multiple opportunities, but we will do another one of those. Now there'll be some partial credit, so it'll be a little easier to score better. All right, but that's this idea of position, velocity, acceleration. All right, let's get out your other packet. And there's one problem. We'll go over more of it, so I want you to hang on to these, but I want to go over the last problem on the first page. Number 11 there on the front page. Again, this brings back some good review type stuff that we need to be able to do, and that's, again, what Chapter 4 is about, is reviewing and utilizing the derivative, applications of the derivative. So all those things we learned previously, we need to be able to come back and do. So this says, it talks about finding the total distance traveled. Now, again, we have a position function, so it's our x equation. We have a particle moving back and forth on the x-axis. So we have position, velocity, acceleration. This is x, x prime, and x double prime. I mean, we just as easily could have a particle moving up and down on the y-axis. And then it would be y prime, and y double. Okay, with t being our input variable. It really fits in easily with what we're going to, the new stuff we're learning today. All right, so this is its position. Now, this sentence threw a lot of you. That just, what does that mean? Find the sum of the absolute values of the differences in position between its resting points. So let's focus on that last part. What's a resting point in this problem? Where the velocity, this line, is 0. Because what we have is a particle starts at time 0 and it moves. And it goes to the right, maybe, and then it stops, and then it comes back to the left, and then it might stop again and go back to the right. We don't know how many times it'll stop and turn around. Every time it might stop, go to the left, stop, keep going to the left. We don't know for sure, right? But if it's going to change direction, it's going to have to stop. So its velocity is going to have to be 0. Okay? So all right, so anyway, so that's kind of a synopsis of what's happening. So tell me what you want to do. Zach, what you're doing on the computer, does it have anything to do with what we're doing here? Okay, so why is it open now? That's what I want. Okay, thanks. Okay. I don't know why. 10 different times I turned there and saw you with that computer out, and it didn't even dawn on me. And all of a sudden I'm sitting there, what in the world? Okay, all right. So what could I do? There's several things I could do first here. Okay, one would be do x prime, because that's the velocity, right? So let's do that. So x prime of t would be t squared minus 2t minus 3. Okay, all right, there's x prime. And set it equal to 0, because we just talked about resting points, so we're interested in where that would be 0. Okay? Now, this might not have been the first thing some of you done. Some of you might have done some other things first. The order we do things here probably doesn't matter. All right. And this looks like an easy old factoring kind of thing. Okay? T minus 3 and t plus 1. And so equals 0, so t is 3 and negative 1. Okay. All right, now -1 I could cross out because we're talking about t being from 0 to 6, so we're not worried about that. Right? Okay. Richard, what were you saying? The distance, but okay, so at 3 seconds the particle is stopped, is what we just found out, right? So were you saying find the distance between 0 and 3?
Yeah.
How do you propose we do that? Do what with the original equation? Put 0 into the original equation. What does that tell you? It's somebody else. What does that tell? Why does he want to put 0 in the original equation? Sam? Okay, so we put a 0 in for t and we get 4. So that tells, so what we have, let's just draw an x-axis. Here's an x-axis right here. Okay, and at time 0, the particle, let me put a 0 in here. So the particle was here at 4. So that's my particle. Okay? It was right there at the beginning. That's where the particle was, on the x-axis. Okay, I'll put it above. Okay, but that's where the particle is at the beginning. That's what we just found out. That'd be good to know, right? Where was the particle at the beginning? Okay, and then you said put a 3 in? Okay, let's do that. So 3 cubed, 27 times a third, that'd be 9. 3 squared is 9. 3 times 3 is 9. Wait, I did something wrong. Didn't I? Oh, no, that's right. That's right. So 9 minus 9 is 0, minus 9 is -9, plus 4 is -5. So what's that mean? So we went backwards. So we went back to here, right? And then he's going to, well, I don't know what he's going to do. He's going to stop, right? Assuming he's going to turn around, but maybe he won't turn around. Maybe he'll stop and keep going the other way, right? But he's going to stop right there, and that would be at t equals 3. Okay, then what? Then plug in a 6. What's this kind of looking like over here? This looks familiar to me. It looks like a list of candidates, doesn't it? We did the derivative. We set it equal to 0. We found a 3. We plugged it back into the original. What else are we plugging into the original? Endpoints, right? Endpoints and stationary points. Put those back in the original. That's when we're finding max and min, right? Max and min. Well, what we're finding here is the max position he was, which means farthest to the right, and his minimum position was when he was farthest to the left. So we're really kind of finding max and min here, aren't we? So really, this is a very similar problem. Okay, so we plug a 6 into the original. Ooh, 6 cubed. It is 216, but this is a no calculator problem. You could be smart about it if you didn't want to do that. You can do the 1/3 times the 6 there and get 2. 6 times 6 is 36 times 2. That's 72. Those of us that grew up in the day before calculators, we learned to get kind of smart about those things, so we didn't have to do big long calculations. But anyway, so 72 minus 36 would be 36, minus 18 would be 18, plus 4, 22. So this thing did turn around and ended up way out here at 22. Isn't that a pretty good description of what just happened here with this particle? Did it ever turn around any other times? How do you know? Yeah, when we did x prime equals 0, we found all the times when the velocity was 0. So it never could have turned around any other times because it never did stop any other time. Now, hopefully this sentence makes more sense then. This sentence says, find the sum of the absolute values of the difference in position between its resting points. Well, what that means is from 4 to -5, I don't care how you subtract it, that's where the absolute value comes in. It went how far? 9. And then from here to here it went 27. So 9 and 27 is 36. So the total distance traveled by this particle was 36. Now, somebody in the other class, when they got to this problem, they had 18 for an answer. Maybe some of you had 18 for an answer on this one. Where were people getting 18 for an answer on this one? Didn't do the resting points. Plugged in a 0 and plugged in a 6. You found out where it started, you found out where it ended, and you subtracted them. It started at 4 and ended at 22, so it went 18. That's displacement. That's net distance traveled. Total distance traveled has to take into account the back and forth. And the way you get the back and forth is you find where it stopped. You find when the velocity or the derivative was 0. Okay? Another thing we could have done here, since this looks like a list of candidates, I remember doing number lines. I remember doing the derivative You guys remember this? We did the derivative, we set it equal to 0, and we put that number on a number line. Say an x prime number line, and we put a 2 and a 4, and we put those back into x prime. Let's do that. Let's put a 2 in here. 2 minus 3 is a negative. 2 plus 1 is a positive. Let's put a 4 in there. 4 minus 3 is positive. 4 plus 1 is positive. What's that tell you about the particle? Left, then right. Now, did that help us? Not really. It didn't help us any more than what we did over here when we did this. But what might have helped us if we'd have done a number line first is what if this would have been plus then plus? We would have known it stopped and kept going, and we wouldn't have had to do this other point here. We could have just said, well, it started at 4, then it went right, stopped, and then kept going right. Then the answer would have been 18. Okay? But on this one, we know it went back to the left, and then it went to the right. And so we would say, well, we need to know where it was at 3, so we plug it back into the original. But you got to understand what plugging into the original tells you. It tells you what position it was at. What does plugging into x prime tell you? It tells you what velocity, which tells you what direction it was going. Okay? So these are all important things to understand with motion. I mean, most of it is stuff we've already talked about. Okay, but maybe not as much in context of this problem. Yes?
So the number lines, if it went past the 3s, it was going forward, but we wouldn't know if it came back a little bit and then kept going forward.
Say that again on the number line.
So it's positive.
Right. Without plugging in your 0, you would still need these values because this tells you goes left and right, but we don't know. Yeah, it might have went way left and then come back right just a little bit, and not even got back to where we started. But we know it didn't have to turn around any more times. We know it only didn't go back and forth any more than that because this is the only time it stopped. Okay, so we definitely know that. All right. We'll take a 60-second break to do a couple of things here. Stand up and stretch. Bring your clickers back up here, put them in the right spot, and get out, dig in your folder, and see if you can find the old worksheet we did called Lion and Ranger. Lion and Ranger. So stand up, stretch, put your clickers away, and get out that worksheet while I eat my donut.
His bench press even hurt your back?
Not bad.
Like right here.
Maybe, yeah.
You're benching it very
Sounds
fun.
You know what? I scraped my window when she yelled and I'm sore.
Oh my god.
No, but I had to reach up tall and really fast and hard. It was really tough this morning. But really
Hey, I'm not going to say anything because that would be me. That would be me.
I was laughing in my head because I was like, I know it is. Lion and Ranger.
Lion and Ranger.
I didn't get very far. Oh, I didn't.
Okay, we've got number
Well, I
3.
didn't have like any because I'm sick. I don't think I
My drawing is pretty terrible. Don't judge. Did people call you Richard Nixon What do they call you? I feel like Richard Weir.
It's always fine.
I don't think I'd like to be called Rich. But maybe Richie. Wait, what's short for visitor?
All right.
Okay, that's I have an uncle or something named that. He's a great uncle. He's a great uncle.
He's a great uncle in the sense that he's a great guy, or he's
No, like-
literally a great
like
uncle.
My mom, like my mom.
That's-
I only have one uncle. And it's a Vance.
All right.
It's a Vance.
Okay, listen up. That's now I meant to go over these obviously a little sooner than this right now, But this was after quiz. We worked on this, and we were going to go. But I knew it would tie in with what we're talking about today. The title of section 4.4. I'm looking at a lot of blank papers. Does anybody have something filled out on this?
Yes.
Yeah, I have part.
I have
Okay,
a little
good.
bit, I don't have
Okay.
anything.
See, look, second block was doing well.
Looks
Okay,
like
well,
a successful.
Okay.
Still looking back.
I suppose. Now, the title of section 4.4. Now, we've been doing some review here on. Uh-oh. What happened, Matt? Are you still logged in?
Yeah.
Okay, I don't know what just happened there. Yeah, you might get off the hook now. Oh, you were. Carrie is. You were just the presenter. She's not the presenter.
She's so good.
She was good. Riley is the presenter today. Hey, cool looking graph. All right. What? Now, clear the scratch pad. Go up this Lion and the Ranger situation. It talks about parametric equations. That's the title of 4.4. So now we've been talking about midterm review and stuff, although the last couple of questions have been kind of tying in with what we're doing now. But this, now what we're talking about is going to be on the next quiz. All right? This is going to be on the next quiz, and you are going to have to be able to work with parametric equations. Now, what happened with the Lion and the Ranger, to refresh your memory for those of you that actually worked on it, we had this picture of this park, and the x-axis represented east of the ranger station, and the y-axis represented north of the ranger station. So the ranger station was at the origin, all right? And it went 120 some miles to the north, and it went like 80 miles, or excuse me, to the east, and it went like 80 miles to the north. And what we had is the ranger was like 100 miles east of the ranger station, but he was walking back towards the northwest, or driving, or whatever. Okay? Now he was going back towards the northwest. And he was going at, and they gave the information in kind of a strange and interesting way, if you read it. It said that he was going 0.5 miles west for every 0.6 miles north. He was doing that each minute. So in a minute, now he was actually walking on the diagonal, but he was going 0.5 miles each minute west and 0.6 miles north each minute. And the Lion was going 0.3 miles to the east and 0.1 mile north at that rate. Okay? And so then the question was, are they going to cross? Are they going to cross paths? Are they going to meet? That kind of thing. Okay, now crossing paths and meeting, as we'll find out, are actually two different things, okay, in the sense of this problem. So if we look at the front half of the worksheet, most of that was just plain old basic algebra kind of questions, right? The equation of the line, because you have a couple of points, and you could calculate the slope. And what's the slope of the line's path here? It'd just be 0.1 over 0.3, right? Every minute, so it's 0.1 over 0.3, which would be 1/3. And the Ranger is 6/5. Now, it'd be negative because the Ranger's is in this direction, so his would be a negative slope. So you could write the equation of the line, you could see if they intersect, right? That's just basic algebra. See if they intersect. It turns out that they did intersect at, what was it, 45? Those of you that worked it, where'd they intersect? 4566 was the point where they actually intersected. Okay, so the line was kind of going up like this, and the Ranger was kind of coming this way, and then they crossed like so. All right, now, down at the bottom, if we were to take, let me get a, oops, let me get a, oh yeah. So let me get a new page of here. So basically we have this. All right, so the Ranger started down here at the point 100, 0. Okay? And then he headed up this direction. So 1 minute later, what point was he at? (99.5) and 0.6. Because remember what he was doing. He was coming back 0.5 and up 0.6 every minute. And so 1 minute later, he would have been at what? 99 and 1.2. Okay? So as we look at this, and this is what, at the last table at the very bottom of the worksheet, you were supposed to fill in, is this pattern. Well, what we're going to do, and this is what a parametric equation does, is it treats the horizontal component and the vertical component separately. Now, if you've been in physics class, you know about vectors, horizontal and vertical components and stuff. It's very much related to that. Okay, so what we're doing is we're going to talk about the horizontal and the vertical position of the Ranger. Now, contrast that with what we were doing earlier. You've got the x-axis here, you've got a particle moving back and forth. That's just one-dimensional motion. The particle just has horizontal movement, has no vertical movement. But here we have two-dimensional motion, like on a diagonal. It has both horizontal and vertical movement. Okay, and we're breaking it down into those two parts. So we will have both an x and a y equation for the line and for the Ranger. Unlike the particle, which only has x motion. Its y equation would be 0, because it had no y position, or its y position was always 0. So this is how this works. So we looked at the coordinates of the Ranger, and now let's look just at the x's. Well, how would you generate these values? Well, it looks like the Ranger's x coordinate is 100 minus 0.5 every minute, right? Every minute. Every minute, the Ranger's x coordinate goes down by 0.5. So in the box, down at the bottom of the page, at the very bottom row, that's what you would have had for the Ranger. Now, what's his y coordinate doing? His y coordinate is starting at 0, and it's increasing by 0.6 every minute, and t is the minutes. So we really have three variables involved in a parametric equation. We have x. Now, keep in mind what x is and y. X is miles east of the Ranger station, and y is miles north. Now, that's not a normal position function. Normally, when we do a position function, we have miles on the y-axis, and we have time on the x-axis, right? But here we've got miles. We've got miles on the x, and we've got miles on the y. So x and y are both miles, but the t then is the minutes. T is nowhere in the picture, right? All right, and then we got the line. Okay, so the line, now I actually want to go back here. I'm going to write these in here. So for the Ranger, we had, what was it, 100 minus 0.5 t, and then this was 0.6 t. And so then what would the lion's x coordinate be? What was his x coordinate at the beginning? No, his x coordinate. 0 plus, he goes 0.3 horizontally every minute. So it'd be 0.3 t. And what would his y coordinate be? Where's his y coordinate start? His y coordinate starts at 51. Right? He started 51 miles north of the Ranger station. So his y coordinate in the beginning would be 0, 51. But then what happens to his y coordinate here? It grows up by 0.1 every minute. Okay? Every minute. All right. So these pair of equations is called a parametric equation. The word parametric comes from parameter. The t, that third variable, is called the parameter. Okay, so x and y are both functions with respect to t. The horizontal position of the person and the vertical position of the person are both changing with respect to time. This is called a parametric equation. Okay, Riley, you're going to be up here now. So, we're going to go ahead and graph those two things on our calculator using parametric. So get into a graph screen. So go ahead and go to your graph screen. All right. Now let's set our window first. So go to our window settings. And we want our window to look just like the picture on your paper then. So our x is going to be the miles east of the Ranger station. So we could say, let's do negative 10, just so I like to see the boundary there. So let's do negative 10. Oops. Let's put negative 10, and then how far right? How far east? 100, on your paper it's like 120, I think, isn't it? A little far. Let's go a little past where the range is at. So let's go 120. And then the y, what would we want? Let's do negative 10 again for the minimum. And how far up? It's like 80, I think, on your paper. So let's go 80. Okay? And then hit OK. All right? So this gives us a pretty good looking picture like what's on your paper. Okay? This is a picture of the park where the ranger and the lion are walking. All right. So now we need to change this and get into parametric mode. So we're going to go to our menu, and we're going to go to graph entry and parametric, number 3. Okay, and notice what you're presented with. You got x1 of t, y1 of t. T is going to be your input variable, just like we think it should be. So let's do the ranger first. So the ranger was 100 minus 0.5t, and the y equation was 0.6t. Now, before you're out of there, notice the bottom line. Because we've already set our x and y window, but x and y were both miles. We need a way to set our time boundary. Okay? Well, how long do we want the lion and ranger to walk? I think those of you that worked the worksheet, that answer is somewhere in there, question 3 or 4. There's a time answer in there.
This is how
How long does it take for them to reach? Okay? What'd you have there? 110 for one of them and 140. I think it was 150. I think it's 150. But anyway, it's somewhere in there. But now, just for the heck of it, type, go down here, Riley, where it says t, and let's change that 6.28 to 10. And just leave the t step as 0.13. Okay, now go ahead and hit enter and graph this. Because it's kind of cool what this looks like. Why did it do that? So what does that show?
10 minutes.
Yeah, that's where the ranger was in 10 minutes, right? Parametric equations is literally modeling the walking of the ranger. Starts here, and it's going this way. If you hit trace right now, go to menu and trace, and graph trace, and hit type a 0. Type a 0. Now, when you do a graph trace in parametric mode, it's based on time. So when she types in a 0, it tells me where the ranger was at 0. Now hit the right arrow. Okay? And keep hitting the right arrow. And notice that's the direction the ranger's walking. And so he's going. And at 10 minutes, that's all the farther he was. Okay, so go ahead and hit tab, or escape out of that, or hit tab so your equation comes back up. Tab again. There you go. Arrow up. And now let's change that 10 to, say, 180. Let's do 180 minutes because we need to see, we need to give the ranger long enough to get farther. So we go ahead and hit enter. So you have to understand what T stands for in your problem to be able to set that value. Okay, so here it is. So now here's the ranger, and he's up out of sight in 180 minutes. Okay, now let's go ahead and put the lion's equation in. We'll put that in x2 and y2. Okay, so what was the x equation for the lion? 0.3t, and then 51 plus 0.1t. So see what's happening with a parametric equation, you have separate equations for the x-coordinate and the y-coordinate, as opposed to our normal equations we're used to, which just involve the x. If x is this, y is this. If x is this, y is this. Now what we're saying is if t is this, then x is this and y is this, right? You see the difference? At this time, we have both an x and a y value, which is where the thing is. Okay, go ahead and change that to 180 again, the t, the 6.28. And hit enter. So clearly now we can see that they do cross. But the question is, where are they at various times? So you said 110, right? So type in, so go to trace right now. Go to trace and let's do graph trace and type in a 110. 110 minutes. And sure enough, that's where the ranger is. That's when the ranger gets there. But now hit the up arrow. That's how you get to the other graph. Hit the up arrow. And now type in 110. Because now we're on the red graph. We type in 110, that's where the lion was. See, the lion wasn't there yet at 110. Now if you type 150, this tells you where he was right here. Type 150 into there. Now the lion was there at 150. Okay, 4566. Okay, so parametric equations can tell us a lot more about the situation. If we just graph those two lines like you did on the front side, you just graph their two paths, you didn't know where they were at various times. You just knew their paths crossed, but you didn't know where they were. But parametric equations can give us that information. Okay, now what are you going to need to know and be able to work with? Well, first of all, you got to understand what the different equations stand for. All right, there's three different things that we need to know about parametric equations. This is what we're going to put in our notes here in a second. Now, the one thing I left off, on question number 6, on the front of your worksheet, what did question number 6 ask? Yeah.
What rate do the lion and the ranger each travel per minute?
At what rate are they traveling per minute? Now, up until right now, if I ask you a question about rate per minute, you would think of doing what? You'd think of a derivative, right? Because derivative is rate and derivative is velocity. We've got to be really careful now with parametric equations. Because if you do the derivative, I mean, number one, what do you do the derivative of? And number two, what are your units on your derivative? Okay? We've said rate and slope are the same thing. Well, that's not really true here. Because what did we say the slope of the lion was here? 1/3. It was just this over this. But what's the lion's speed? Well, the lion's speed, and for you guys that did the worksheet, how did you calculate it here? Which is a Pythagorean theorem, right? In 1 minute, this is how far the lion had went in 1 minute. Well, how far is that? Well, it's 0.1 squared plus 0.3 squared, wouldn't it be? I mean, because in 1 minute, he went 0.3 this way and 0.1 this way. So in 1 minute, he had went this far, which turned out to be like 0.31 to something, right? Miles per minute. Is that the same as his slope? That is not the same as his slope. And the units wouldn't even be the same. If you do the slope here, this is 0.1 miles north divided by 0.3 miles east. Now, it's still a rate. This is very important now. That slope is still a rate. It's just not the rate we want. It tells you that he traveled 1/3 of a mile north for every mile east. That's a rate. But it's not a speed. Okay? So it's very important to understand the difference. So the speed of the lion, actually, on a two-dimensional motion now, speed comes from combining the horizontal velocity, because that's what this is a horizontal velocity, and the vertical velocity. Now, let's talk about where derivative is the same as the speed. It would be on each of these individually. Here's the lion's horizontal velocity. Here's the lion's horizontal equation. What's the derivative of his horizontal equation? 0.3. Do you see how that would be x prime here? That would be x prime of t. That would be his horizontal velocity. What would be his vertical velocity? Be the derivative of this equation. 0.1. So his horizontal and vertical velocities are derivatives of his horizontal and vertical position. So now we not only have position and velocity equations, we have two of them. We have a horizontal position and a vertical position, and then the derivatives of those would be his horizontal velocity and his vertical velocity. But his actual speed would be the Pythagorean theorem combination of his horizontal and vertical velocity. And that's a formula we're going to write down here in a minute that you're going to need to know. And then, of course, we got the slope, which we said is just this divided by this. Okay? All right. So those are some things we use there. So let's get your notes out and let's write these things down here. And we'll just take one at a time. We got 3 different things, and then down in the corner I've written the equivalent part that had to do with the line problem. Okay? And so we can kind of get a sense of what we're talking about here. But these are the 3 things that for the quiz you're going to have to be able to know, be able to do. Now you're also going to have to be able to graph a parametric equation like Riley just did. You're going to have to be able to go into your calculator, go into parametric mode, be able to type the equation in. Matter of fact, on tomorrow's homework, it's a problem with the parametric equation. You're going to type in your calculator, and be able to use it. Okay? All right, so parametric equations. First of all, parametric equation is made up of two equations, x of t and y of t. By far, the most common application of parametric equations is motion, two-dimensional motion. Okay? Where we have both a horizontal component and a vertical component. So we're talking about diagonal motion. Okay? Because most of the time we don't move just horizontally or just vertically. Okay, we have components. All right, so the first thing you're going to have to know is horizontal and vertical velocity, which is simply x prime and y prime. Again, this goes back to position, velocity, acceleration. Think of the parametric equation as position functions, two of them. There's a horizontal position function and a vertical position function. And together they give the position of the particle, both its x and its y position. So therefore, the derivative of those would be the horizontal and vertical velocities. Now, notice I've written dx dt, dy dt. It's going to be very important now to separate this out and think about this from a derivative standpoint. It's not going to be enough for us to just say x prime and y prime anymore, as you're going to see with number 2 there. Because if I say y prime, what do I mean? Do I mean dy dt? Do I need the y rate with respect to time? Or am I talking about the dy dx, the rate of change of y with respect to x? Those are two different things. They're both called y prime. So you got to be careful. Okay? So you're going to see dx dt and dy dt used a lot. All right? Now with the line, remember what that was? That was what they gave us. X prime was the 0.3 miles per minute, and y prime was the 0.1 miles per minute. That was the horizontal, and that was the vertical movement. Okay, let's talk about number 2 here. Slope of the path. Now that's different than the speed. That's different than the horizontal vertical velocity. That's where we did the 0.1 over the 0.3. Okay, that's where we took the y over the x, rise over run. Okay, now we can get that though, and think about that now. That's your change in y over change in x. That's the slope of the path, change in y over change in x. We could get that by doing the vertical derivative divided by the horizontal derivative. Really, that's what 0.1 and 0.3 were here. They were the horizontal and vertical velocities. Now, here's where I like the dy dt notation, dx dt, because think about this. If you took dy dt divided by dx dt, what would happen? Algebraic. Yeah. Invert and multiply kind of thing, the dt's would cancel, and sure enough, you'd end up with dy over dx. So it kind of makes sense. So slope of the path, this is just a formula you're going to have to memorize. Okay? dy dx, the slope of the path, is simply the y derivative on the parametric equation divided by the x derivative. Okay? That's not bad though, because y is always on top when you're doing slope, so it makes sense. All right. And then finally, another thing we'll be interested in is the speed of the object on the path. How fast is it actually traveling? And that's when we did with the lion, that's when we did the Pythagorean theorem thing. We had to take into account both its horizontal and its vertical velocity. So we took its horizontal velocity, 0.3 squared, plus its vertical velocity, 0.1 squared, and did the square root of that, and that's where we got its actual speed on the path. So x prime squared plus y prime squared, and then the square root of that is the speed of the object. Because if we want to know how far it travels on its path, we're going to need to know how fast it's going. Right? Kind of a distance equals rate times time. All right? So those are the three things we need to be able to separate out. This is where it becomes vitally important, just like I was talking on that one problem on today's packet. You got to understand, what's the x equation represent? What's x prime represent? Well, if you just keep in mind that x is the horizontal position and y is the vertical position, then it makes sense that x prime is a horizontal velocity and y prime is a vertical velocity, which means what direction is it going up and down, and what direction is it going this way? Tell me this. What direction, use north, south, east, west, those kind of things. What direction would something be moving that had x prime negative and y prime positive. X prime negative, y prime positive. Northwest, right? If x prime's negative, means it's going left, west, and if y prime's positive, means it's going up. So it'd be northwest, right? So individually, these tell us horizontal and vertical. Together, then they give us a direction, right? And the bigger it would be, okay, the bigger y prime is, the more north it would be going, you know, and those kind of things. All right, you would get it, or the faster, the more it's going north compared to how fast it's going west, and so forth. Okay. What if x prime was 0 and y prime was positive? Be just going north. It would have no horizontal movement, right? Now we talked about when x prime is 0, it's at rest. So in two-dimensional motion, if the derivative here is, if one of these is 0, does it mean it stopped? What would have to be true for it to be stopped? They'd have to both be 0. It couldn't be moving horizontally or vertically, right? But if one of them's 0, it's just like one-dimensional motion. Okay. So you're going to have a worksheet here with a little bit to do. Now I do want to show you just one more quick thing. You guys have done some parametric equations and didn't know. Here's a parametric equation right here. Okay, Riley, you're going to type again on this one. Delete out the first two that you had, okay, while we're talking about it. Does this look familiar? X equals cosine and y equals sine? What is that? Where does that come from? That's a unit circle, isn't it? But think about this as motion. This is position. Let's talk about it t equals 0. When t equals 0, what's cosine of 0? 1, so the x would be 1. And, oh, oops. And what's the y? 0. So the x is 1, the y is 0. That'd be right here. Right? T wouldn't necessarily be time here, but it would be your radian angle, your radian. But this should be unit circle. Okay, so Riley, let's put those in. So let's put cosine t in here. And you get a sense of why the default entry for t is 0 to 6.28? Right? 2 pi, right? That would give you a full unit circle, wouldn't it? If you did 0 to 3.14 here, what would you get? You just get the pi. You just get the top half of the circle, right? So we'll leave it. Okay, go ahead and hit. Now our window's no good. Go ahead and hit enter, and we're gonna have to fix our window. It's this little tiny thing down here. Go to your window settings, and let's do like -2 to 2 on both of them. On our settings, let's go -2 to 2. It should be a nice unit circle, except for one problem. It doesn't look like a circle. Why is that? Yeah, this is wider, and it's wider by a factor of about 1.6. So go back to your window settings again, and let's make the x 1.6 times as big, roughly. So what would we make the x's?
You just put in the time table.
Yeah, oh yeah, actually could just say times 1.6, but 3.2, -3.2, 3.2. That's true. You can, it will actually multiply, I think, in there for you. So -3.2 to 3.2, and now we should get a little better looking picture. Unit circle, and then hit trace. One last thing here. Let's just trace around. And so when we go to trace and we type in a 0, sure enough, it starts right there. Now just hit the right arrow, and it should just go right along, like you would expect the unit circle to go along. And this should be about pi halves, 1.57, and over here should be about pi, right? T is the input. So neat way to do a circle. Matter of fact, it's even easier. Remember ellipses? Right? Remember the complicated equation you have with the ellipses, x squared and y squared and subtractions and stuff? Go in, hit tab, and go into your thing again. To make this an ellipse, all I want is the x to be twice as big as the y. I just want to make this go out twice as much. How could you do that? Put 2 in front of the cosine, right? We just want the x coordinates, instead of going -1 to 1, we want the x coordinates to go -2 to 2. So put a 2 in front of the cosine, you got an ellipse. There's an ellipse equation. So all you have to do. So cosine and sine, since they both go -1 to 1, you get equal radius on both the x and the y. You want unequal radius, that makes an ellipse. You can do all kinds of cool graphs, and on your homework today, we're going to do a parametric equation that has that graph. Right there. Okay, if I can find the